Welcome back to the AI Research Roundup. I am your host, Alex. Today, we're diving into a paper from NVIDIA called Cosmos Drive Dreams, Scalable Synthetic Driving Data Generation with World Foundation Models. The big challenge for autonomous vehicles is getting enough training data, especially for rare and dangerous situations, what we call edge cases. This is where the paper's main contribution comes in. It introduces a synthetic data generation pipeline that uses a World Foundation model, which is a massive AI trained to simulate the physical world, to generate realistic driving videos. This allows researchers to create countless tricky scenarios on demand, helping train car AIs to handle the unexpected and improve their overall safety. And for those looking to build on this research, what's really great is that the authors have released the official code for this work. The repository has the full synthetic data generation pipeline, including their model weights, various toolkits, and a huge dataset with over 80,000 generated clips. Each clip comes complete with HD maps, which are high-definition maps providing precise details like lane markings, and also LiDAR data. LiDAR, which stands for Light Detection and Ranging, is a sensor that uses lasers to build a detailed 3D map of the car's surroundings. Alright, so this first figure really brings that whole pipeline to life. On the left, it shows what the paper calls the autonomous vehicle data flywheel. It's a continuous feedback loop. You use Cosmos Drive Dreams to generate vast amounts of data, train your models, and then evaluate them to find weaknesses. Those weaknesses then guide the creation of new, more challenging data, and the cycle repeats. On the right, we see the results. Incredibly diverse scenes, multi-view camera outputs, and crucial corner cases like near collisions or sudden stops, complete with the corresponding LiDAR sensor data. So drilling down into that pipeline, this figure shows the 4 key steps. First, it starts with either structured labels, which are like a digital blueprint of a scene, or a real video. Both are used to create a condition video, which is a kind of skeletal guide for the AI. Next, a prompt rewriter creates diverse scenarios, like making the scene snowy or rainy. Then, the system expands this into multiple camera views. Finally, a vision language model, an AI that understands both images and text, performs rejection sampling, automatically tossing out glitchy videos to keep the final dataset clean. Okay, so that was the general process. This figure shows the specific model suite that powers it. The team starts with a general World Foundation model, and then fine-tunes it on real driving videos. This post-training creates several specialized AIs. One model handles precise layout control, generating a video directly from a high-definition map. Another performs multi-view expansion, creating a full surround view from a single camera feed. And there are even models that can annotate a random video with map data, or generate a realistic LiDAR point cloud from scratch. Alright, so digging even deeper, this figure shows us the architecture for one of the core generation models. It uses what's called a diffusion transformer, which is a powerful design that basically starts with random digital noise and progressively sculpts it into a clean, realistic video. You can see it has 2 main pathways. The main base model on the left is doing that core generation work. But critically, it's guided by the control net on the right. ControlNet is a specialized network that takes our specific conditions, like the high-definition map or LiDAR data, and injects that information into the base model, ensuring the final video precisely matches the layout we want. And here we see the incredible power of that ControlNet architecture. This figure shows the results from their precise layout control model, the Cosmos Transfer 17B Sample AV. On the far left, you see the exact same high-definition map being used as the structural input every single time. But then, just by changing the text prompt, the model creates entirely different outcomes. We can see it generate a scene with steady rain, a chaotic one with a huge fire, and even a beautiful, calm street lined with blooming sakura trees. This really highlights the model's flexibility. So, where the last model focused on creating scenes from a map, this next model tackles a different challenge. This is the Cosmos 7B Single 2 Multi-View Sample AV model, and its job is to perform multi-view expansion. This means it takes a video from just one camera and intelligently generates what all the other cameras, like the side and rear views, would have seen. You can see it in action here. The top rows show a sunny scene evolving over time. Then, for the bottom rows, the model was prompted to make it a snowstorm, and it generates that weather consistently across all the different camera angles. Okay, so this diagram shows the specific architecture for that multi-view model. It's actually adapted from the previous model we saw, still using a base model in an MV control net. The main difference is the introduction of these special multi-view transformer blocks. Inside each block, the model uses a technique called cross-attention. This is a key mechanism that allows the model to weigh the importance of different inputs, so it can pay close attention to the multi-view text prompt, like add snow, and apply that change consistently across all the different video feeds it's creating. As we've seen, the Cosmos Drive Dreams project is a really powerful step forward for generating synthetic driving data. By using these world foundation models, the researchers can create incredibly diverse and controllable scenarios, from precise layouts based on maps to expanding a single video into a full multi-view scene. This ability to generate high-quality, varied data is crucial for training more robust and safer self-driving systems. Well, that's all for this AI Research Roundup. Thanks for tuning in, and I'll see you next time.